Build a simple RAG pipeline in Python, end to end. By the end, you will have a tiny retriever that tokenizes text, ranks documents by similarity, and constructs a short context for answering a query. You will see how retrieval reduces hallucination, and how to glue retrieval to a simple extractive answer. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced in simple Python. RAG matters because it boosts relevance. It pushes model responses toward real text instead of fabricated facts. The core metric it optimizes is precision of retrieved context for a query, which directly improves answer accuracy. The trade-off is cost and latency. More documents or a heavier index raises memory and search time. For practical scale, this simple approach works well for a few hundred to a few thousand short documents before you need an ANN index. At a high level, RAG pairs a retriever and a reader. The retriever finds candidate passages that match a query. The reader uses those passages to produce an answer. This shines when your data is grounded and relatively static. The limitation is retrieval quality. A bad match still pushes the reader astray. We will build a minimal pipeline that tokenizes a tiny corpus, finds the best match with a set similarity, ranks the candidates, concatenates the top pieces into one context, and extracts a short answer from that context. First, we prepare the text by splitting into tokens and building a small sorted vocabulary. This snippet tokenizes a tiny corpus and prints its sorted vocabulary. It normally lowercases and splits on white space, keeping only simple words. The point is to show how raw text becomes items you can compare. A sorted vocabulary helps you inspect coverage and spot noisy tokens. If you made tokenization coarser or finer, the vocabulary would shrink or grow accordingly. Coarser tokenization tends to improve match stability, but can lose nuance. Finer tokenization picks up phrase differences, but may fragment matches. This step is a lightweight way to check your corpus before building retrieval. Next, we compare the query to each document to find the single best match. This snippet computes Jacquard similarity to retrieve the best matching document. Jacquard similarity is the size of the intersection of two token sets divided by the size of their union, which measures shared token overlap in plain language. The snippet takes the query tokens and each document token set, computes that ratio, and returns the highest scoring document. Jacquard is robust for short text and literal overlap. It will fail on paraphrases, so if you need semantic matching later, you would swap the metric. For small experiments, Jacquard gives an interpretable baseline and is very fast. Now we expand that one best match into a ranked list so we can pick several candidates. This snippet ranks documents by similarity and prints the top 3 scores. It calculates the same similarity for every document, sorts them from highest to lowest, and shows the top 3 entries and their scores. The adjustable parameter here is the number of top results you keep. If you increase it, you include more context at the cost of noise and longer input for the reader. If you decrease it, you keep the context tight, but risk missing supporting facts. Use 2 to 5 candidates as a typical sweet spot for small models and short documents. Next, we build the retrieval context by joining the top candidate passages into one block. This snippet builds a retrieval context by concatenating the top K documents and labeling them with simple separators. It takes the ranked candidates, picks the top K, and combines them into a single text blob that will be fed to the reader. The key parameter is K, which balances context breadth and token budget. Larger K gives the reader more material to draw from, which can increase recall, but may exceed model input limits or introduce contradictions. Keep the concatenated context focused and trimmed by removing very short or irrelevant passages before joining. Finally, we run a simple extractive step over that context to produce an answer. This snippet returns a simple extractive answer from the retrieved context, by searching for the most relevant sentence or phrase that overlaps with the query. The snippet can use a scoring function, such as overlap of query tokens with each sentence, and return the highest scoring sentence as the answer. For an extractive reader, the main parameter is maximum answer length. Shorter max length forces concise answers, but may cut off needed details. This minimalist reader reduces hallucination because it only returns text found in the retrieved context, rather than inventing new content. Recap: RAG combines retrieval and reading to ground answers in real documents. Use it when you care about factual accuracy and have a reusable corpus. Caveat: retrieval quality limits the whole system. Next step: scale this pipeline by replacing Jacquard with a semantic embedding index and adding an ANN search-like face. Or tune the retrieval depth by experimenting with the number of candidates and measuring answer accuracy and latency. If practical AI engineering helps you, subscribe and watch the AI engineering videos.